On November 8, 2025, astronomers witnessed an event that left them stunned. Comet 3I Atlas suddenly erupted, not gradually brightening like a typical comet, but exploding violently into space. Powerful jets of plasma, 5 distinct streams, possibly more, burst outward from a single point nearly 1.5 billion kilometers away. This wasn't supposed to happen. Not at this distance from the Sun, and not so soon after perihelion. Every model of cometary behavior suggested it should have remained stable at this stage. But late on November 8th, Austrian astronomer Michael Jager captured an image that changed everything. His telescope, aimed at the pre-dawn sky, recorded a dramatic transformation. 3I Atlas was no longer a quiet wanderer. It had come alive with raw energy. For months, scientists had tracked the comet carefully, charting its speed, rotation, and chemical makeup. They believed they understood it, until now. So what could cause an interstellar object, formed beyond our solar system, to suddenly unleash this kind of power? Stay tuned, hit that like button, subscribe if you haven't already, and let me know in the comments where you're watching from. Chapter 1. The Eruption. The image captures the comet's coma, that luminous shroud of gas and dust that envelops its solid core. The actual nucleus, though, remains hidden from view, too tiny, too distant, and buried deep within that glowing cloud to be seen directly. What appears before us instead is the shimmering mist of vaporized material flowing outward from the comet's surface, and within that mist, distinct jets emerge, one extending forward toward the Sun, another stretching upward, while 3 others fan outward in different directions, forming a complex fractal-like pattern that almost looks intentional. But what makes this particular moment so striking is the sudden transformation. For weeks, 3I Atlas showed almost no activity at all. It had slipped behind the Sun on October 21st, entering what astronomers call superior conjunction, the point at which a celestial object passes directly behind the Sun, as seen from Earth. During that time, the comet was completely hidden from us. The Sun's overpowering brightness made direct observation impossible. All we could do was wait. Mars orbiters managed to catch brief glimpses of it during a flyby on October. Meanwhile, NASA's Stereo spacecraft and the SOO observatory tracked its path through September and October, using coronagraphs, special instruments designed to block the Sun's glare. But from Earth itself, there was nothing to see. Then came October 29th, the date of perihelion, its closest pass to the Sun. Even then, nothing extraordinary appeared. At that point, 3I Atlas was about 1.36 astronomical units from the Sun, roughly 210 million kilometers, placing it just inside the orbit of Mars. Scientists anticipated that solar radiation would trigger greater activity as the comet's surface heated up, more gas, more dust, more jets. But still, no major outbursts occurred. No sudden brightening, nothing until now. So what exactly changed? The answer may lie in timing, energy, and perhaps phenomena we don't yet fully grasp. Over the past few weeks, 3I Atlas has been quietly absorbing massive amounts of solar energy. The Sun's heat didn't just warm its outer crust, it penetrated deep within, reaching ancient layers of ice that had been frozen solid for billions of years. That stored energy has now reached a breaking point and is finally erupting outward. The jets we're seeing today are the visible result of that process. Subsurface volatiles, carbon dioxide, carbon monoxide, and water ice are undergoing sublimation, transforming directly from solid ice into gas. As these gases expand, they burst through weak spots in the surface, carrying dust along with them, and forming the bright plumes we see shooting into space. All of this is fairly typical for comets. What's not typical is the pattern, the timing, and the intensity of this event. For so long, 3I Atlas seemed dormant, and now, suddenly, it has erupted with multiple jets, all at once. Let's take a closer look at Michael Jager's remarkable image. The direction of sunlight is clearly indicated. The Sun sits off to the left. At this very moment, 3I Atlas is moving through space at approximately 68 kilometers per second, gradually slowing as it drifts away from perihelion. But the jets themselves don't appear random. The forward jet, the one pointing toward the Sun, is particularly puzzling. It's narrow, focused, and entirely counterintuitive. Under normal conditions, solar radiation and wind push a comet's material away from the Sun, creating tails that always stretch in the opposite direction. That's fundamental physics, Light pressure and solar particles push dust and gas outward, forming the classic anti-sunward tail. Yet here, one jet defies that rule. It points toward the sun. This phenomenon is known as an anti-tail, and while rare, it's not completely unprecedented. Some other comets have exhibited similar features. Usually such anomalies are explained by the comet's rotation, combined with the geometry of our viewing angle. In some cases, ejected material from the sunward face of the nucleus can create an optical illusion, appearing to stream forward when it's actually being swept back. But in this case, it's no illusion. Observations from multiple independent telescopes confirm it. This jet is real, and it's indeed directed sunward. Why would that happen? One theory is that the comet's internal structure is more intricate than we thought. Perhaps pockets of gas are trapped deep beneath its surface, building up pressure until they rupture, releasing jets unpredictably, even toward the sun. Another theory suggests that the comet's rotation could be generating centrifugal forces, hurling material in certain directions, regardless of solar pressure. Or perhaps simply put, 3I Atlas is unlike any comet we've ever encountered. For now, let's focus on what's confirmed. Michael Hoger released two versions of his image, one raw and one processed to highlight contrast and make the jets more visible. In both versions, the structure stands out clearly: 5 distinct jets, each extending hundreds or even thousands of kilometers into space, blasting dust and gas at hypersonic speeds. And all of this is unfolding in real time, as 3I Atlas journeys through the inner solar system, approaching a point where we'll finally get an unobstructed look from Earth. You see, for weeks, we've been effectively blind. The sun's glare blocked our view, and although Mars orbiters offered fragments of data, we never had the full picture. But that's changing. As November progresses, 3I Atlas moves out of the sun's blinding path, climbing higher in the pre-dawn sky. By mid-November, telescopes across the northern hemisphere will finally have a clear view. What will they witness? If this eruption continues, we might be looking at one of the most energetic and active interstellar visitors ever detected. The jets could strengthen, the comet could expand dramatically, the comet could become a spectacular showpiece, or it could fade just as quickly. Comets are unpredictable by nature. Sometimes an outburst burns bright for hours before disappearing entirely, leaving behind silence. Yet, this case feels different. From the very beginning, 3I Atlas has defied expectations, and this sudden eruption, this violent awakening after weeks of stillness, is just the latest chapter in an unfolding mystery that began on July 1st, 2025, the day this object was first spotted by the Atlas telescope system in Chile. Let's return to that moment. Chapter 2: Discovery and Trajectory. On July 1st, 2025, the Atlas telescope in Rio Hurtado, Chile, detected a fast-moving object streaking through the night sky. Initially, it appeared to be just another asteroid. After all, the heavens are filled with countless drifting remnants of the early solar system, rocks tracing predictable orbits around the sun, unchanged for billions of years. But this one stood out immediately. It was moving too far faster than any asteroid or comet native to our solar neighborhood. The astronomers who recorded it that night knew something extraordinary was unfolding. Its velocity simply didn't match anything we've catalogued orbiting our sun. It was traveling at nearly 58 kilometers per second, faster than any known object bound to the sun's gravity. For comparison, Earth circles the sun at about 30 kilometers, and Mercury, the fastest planet, at around 48 kilometers. Yet this new object shattered that pattern entirely. The closer an object moves toward the sun, the faster it has to travel to keep from being pulled in by gravity. But this particular object wasn't anywhere near the sun's blazing proximity. It was still drifting far beyond Jupiter's orbit, and yet, it was racing through space at 58 kilometers per second. That's not normal. In fact, that single measurement told astronomers almost everything they needed to know. This wasn't a local traveler. It didn't belong to our solar system at all. It was interstellar. Here's what that means. Every planet, moon, and comet within our solar system is bound by the sun's gravity. We orbit because the sun's gravitational pull tugs us inward, while our sideways motion keeps us from plunging directly into it. But there's a specific threshold called escape velocity, the speed required to break free of that gravitational hold entirely. Now, the farther you are from the sun, the lower that escape velocity becomes. Out near Jupiter's orbit, an object doesn't need as much speed to escape compared to one closer in. But 58 kilometers per second was far beyond that threshold. That meant one thing: it wasn't just capable of escaping the solar system, it was already on its way out. And if it was moving that fast while still beyond Jupiter, it could only mean it had entered the solar system from the vast darkness between the stars, interstellar space. It had traveled from somewhere else entirely, crossing unimaginable distances, with enough momentum to pass straight through our system without being trapped by the sun's gravity. Astronomers began tracing its path backward through time, running calculations and simulations to pinpoint its origin, and the results were undeniable. 3I Atlas had come from beyond our solar system. It entered from the direction of the constellation Sagittarius, near the galactic center, after what was likely millions, perhaps billions of years drifting through empty space. And now, purely by cosmic coincidence, it was visiting our corner of the galaxy. This made 3I Atlas the third confirmed interstellar object ever observed by humanity. The first was Oumuamua, discovered in October 2017, a long cigar-shaped body that tumbled end over end and showed no signs of outgassing despite its close pass to the sun. The second was 2I Borisov, found in August 2019, a far more typical-looking comet with ice, dust, and a glowing coma. But 3I Atlas, it was something entirely different. The first detail that caught scientists' attention was its size. Using data from the Hubble Space Telescope and later ground-based observatories, researchers estimated that the nucleus of 3I Atlas was about 5.6 kilometers wide, enormous compared to previous interstellar visitors. Oumuamua measured roughly 400 meters across. Borisov was about 1 kilometer, but 3I Atlas was nearly 5 times larger, with an estimated mass exceeding 33 billion tons. That estimate came from studying how the comet moved through space, specifically, whether it showed signs of non-gravitational acceleration, the subtle push caused when gas jets off a comet's surface. When a comet vents material, the escaping gas acts like a microscopic rocket thruster, slightly altering its orbit. But 3I Atlas didn't show any such acceleration. Its motion followed a purely gravitational trajectory, unaffected by any outgassing forces. This meant the object had to be dense, massive, and structurally solid. Its venting, if any, was far too weak to make a measurable difference. That was the first clue that something unusual was happening. The second clue came from its trajectory. Typically, interstellar visitors enter our solar system at random angles, coming from all directions in space. There's no reason for them to line up with the relatively flat plane where the planets orbit, the ecliptic. But 3I Atlas, its orbital plane was tilted by only 5 degrees relative to the ecliptic, an alignment so precise that the odds of it happening by chance are around 1 in 500. Not impossible, but statistically remarkable. And then came the third clue, its close planetary encounter. As 3I Atlas journeyed through the solar system, it passed surprisingly near several planets. On October 3rd, it swept within 30 million kilometers of Mars, close enough for orbiters around the red planet to capture images. Later, it would pass near Venus, and by March 2026, it's expected to fly within 54 million kilometers of Jupiter. Each of these events, taken alone, could be dismissed as coincidence. But together with the size, the speed, and the near-perfect alignment, the odds began to stretch belief. Either this comet was incredibly lucky, or something deeper was at play. Now, to be clear, most scientists maintain that 3I Atlas is a natural object, a comet made of rock and ice that formed around another star billions of years ago, was ejected from its home system, and has been wandering ever since. That's the most straightforward explanation, the one that demands the fewest assumptions. And in science, that's where we always start, with the simplest possible answer. But simplicity doesn't always mean completeness, because 3I Atlas has displayed several behaviors that are difficult to fit neatly into the standard comet model. So what exactly makes this object so strange? Chapter 3: The Unusual Chemistry. When 3I Atlas was first observed in July 2025, it was still 4.5 astronomical units from the Sun, roughly the same distance as Jupiter's orbit. At that range, an ordinary comet from our solar system would remain frozen, inert, and dark. The Sun's warmth wouldn't yet be strong enough to heat the surface and trigger sublimation, the process that releases gas and dust into space. But 3I Atlas was already active. The Transiting Exoplanet Survey satellite, TESS, had actually captured faint images of it months earlier, in May and June 2025. Before its official discovery, those early frames showed a dim but unmistakable glow surrounding the nucleus, evidence that material was already escaping. At that distance, such activity shouldn't have been possible. So what was driving it? The answer began to emerge through spectroscopic analysis, a method that reveals the chemical makeup of celestial objects by studying how they absorb and emit light. When sunlight passes through a comet's surrounding cloud, or coma, different molecules interact with the light in unique ways, leaving behind identifiable spectral fingerprints. Using this data, scientists can determine precisely what a comet is made of. On August 6, 2025, the James Webb Space Telescope pointed its powerful infrared instruments at 3I Atlas, and what it found was astonishing. The comet's coma was rich in carbon dioxide, far richer than anyone expected. In fact, the ratio of CO2 to water vapor was about 8. That's the reverse of what we typically see. Most comets from our solar system are dominated by water ice, with only small traces of carbon dioxide. Water requires much higher temperatures to vaporize than CO2. So normally, as a comet approaches the sun, the first gas we detect is water vapor, followed later by carbon dioxide as the surface warms further. But 3I Atlas was different. It showed mostly carbon dioxide, with only faint traces of water, and that CO2 was sublimating even at the frigid distances, where ordinary comets remain inert. That's why 3I Atlas became active so early. Carbon dioxide sublimates at much lower temperatures. It behaves like dry ice, vaporizing as soon as it's exposed to even modest warmth. So this object was, in essence, a massive sphere of frozen CO2, sheathed in a thin crust of dust and rock, drifting through space. But as with everything about 3I Atlas, that wasn't the full story. As it continued its long approach toward the sun, something began to change. By late September, spectroscopic readings started to show the emergence of water vapor, and not just small traces, a dramatic increase, a massive surge of activity that signaled a major transformation within the comet itself. Observations from NASA's Neil Gehrels Swift Observatory detected hydroxyl emissions, the unmistakable sign that sunlight was splitting water molecules apart. What stunned scientists was the sheer volume of water being released. Estimates suggested that 3I Atlas was losing nearly 40 kilograms of water every second, the equivalent of a fire hose blasting non-stop. And this wasn't even close to the sun yet. The comet was still about 2.9 astronomical units away, nearly 3 times the distance between Earth and the sun. At that range, sunlight should be far too weak to vaporize ice so intensely. Yet, it was happening, defying expectations. So what could possibly explain this? One hypothesis is that carbon dioxide outgassing started early, fracturing the comet's outer crust. As CO2 expanded and vented into space, it could have cracked the surface, exposing pristine ice buried beneath. Once that deeper ice was exposed, solar heat would begin sublimating it rapidly, releasing torrents of water vapor. Another idea paints a different picture, that 3I Atlas might not be a solid hunk of ice at all, but a porous structure, more like a cluster of icy grains, loosely bound together. If that's true, then sunlight could penetrate deeper into its layers, warming ice pockets that would otherwise remain frozen. Whatever the cause, the result was astonishing. 3I Atlas was emitting water at a rate no natural comet should achieve at that distance. And this was only the beginning, because water wasn't even the strangest thing about it. In August, the Keck telescope in Hawaii detected something completely unexpected in the comet's glowing coma: nickel, specifically gaseous nickel atoms radiating faintly in ultraviolet light. Now, finding metals around comets isn't unheard of. As dust grains heat up and vaporize, they release trace elements including iron and nickel, the ancient remnants of stellar material forged in long-dead stars. But this case was different. The readings showed nickel without any trace of iron. That's bizarre, because nickel and iron are almost always found together, having formed side by side in the same supernovae that seeded the early solar system. New stars and the comets that orbit them form from that same material, meaning their ratios should always be similar. Yet 3I Atlas defied that rule. It was releasing about 4 grams of nickel per second. but no detectable iron at all. Nothing like this had ever been observed. Some scientists proposed that the nickel might be taking the form of nickel tetracarbonyl, a rare and volatile compound that forms when nickel reacts with carbon monoxide at low temperature. Since nickel tetracarbonyl is a gas, it could easily escape into space, unlike heavier solid iron particles that stay trapped inside. But here's the catch. Nickel tetracarbonyl is something we've only ever created in Earth-based industrial process. It's never been seen occurring naturally, until now, possibly. That explanation remains speculative, fitting the data but not confirmed. What is confirmed is that 3I Atlas released nickel without iron, an elemental imbalance that reveals how little we truly understand about its internal chemistry. Then, just as mysteriously as it began, the situation changed. For several weeks there was no trace of iron. Then by late September, iron emissions suddenly appeared. Not much, but enough to measure. Over the span of days, the nickel-to-iron ratio normalized, resembling that of an ordinary comet. It was as if 3I Atlas was evolving, transitioning from alien to familiar, but doing so in a way that broke every model scientists rely on. Let's recap what we know so far. 3I Atlas is an interstellar comet roughly 5 to 6 kilometers across, with a mass exceeding 33 billion tons. It's racing through the solar system at 58 kilometers per second, following a hyperbolic trajectory that will eventually carry it back into interstellar space after its solar encounter. It became active unusually early, venting carbon dioxide from distances where typical comets remain frozen solid. Then it began ejecting massive plumes of water vapor, far more than any comet at that distance should. And to top it off, it displayed that bizarre metallic fingerprint, nickel without iron, later followed by a sudden shift to normal level. Each of these findings challenges what we think we know about how comets behave. None of it's impossible, but together they describe an object that doesn't quite fit the standard picture of a natural body. And that brings us to the next mystery, the jet. Chapter 4: The Anti-Tail and the Jets. In late July and early August 2025, astronomers began noticing something peculiar in images of 3I Atlas, a tail that was pointing the wrong way. Normally, when a comet approaches the sun, solar wind and radiation pressure push dust and gas away, forming a tail that always extends away from the sun. That's basic physics. The solar wind, a constant stream of charged particles like protons and electrons, blows outward through the solar system at hundreds of kilometers per second, sweeping the comet's debris backward. But 3I Atlas didn't follow the rules. It had a tail pointing toward the sun, an anti-tail. This anomaly was first captured by the 2-meter twin telescope at the Teide Observatory in the Canary Islands. On August 2, 2025, astronomers photographed a faint, narrow jet of material stretching roughly 10,000 kilometers from the comet's core, and astonishingly it pointed directly sunward. While anti-tails have been observed before, they're usually optical illusions caused by perspective, the way sunlight and geometry make a normal dust structure appear forward-pointing. But in this case, that explanation didn't hold up. Astronomers ruled out optical distortion. The anti-tail of 3I Atlas was real material, flowing straight toward the sun. So what could cause that? One theory points to the comet's rapid rotation. If 3I Atlas spins quickly enough, centrifugal forces could fling jets of gas and dust in non-traditional directions, even forward relative to its orbital path. Another theory focuses on structural weak points, regions on the comet's surface where trapped gases like CO2 build pressure until they burst through. When that happens, the gas erupts violently, shooting out plumes of material. Depending on the location of these weak points, some jets might just happen to fire toward the sun, rather than away from it. That explanation fits the evidence, at least for a while, because as September unfolded, something remarkable happened. The anti-tail vanished, replaced by a normal tail. Images from the Nordic Optical Telescope in Spain documented this change. In early September, the anti-tail was still clearly visible. By mid to late September, it had completely disappeared, and in its place, a broad fan-shaped tail formed, extending away from the sun like every other comet. Once again, 3I Atlas had changed its behavior, dramatically and unpredictable. When the sunward jet faded, and a normal tail reappeared, it revealed something crucial. 3 Atlas wasn't maintaining a steady level of activity. Its behavior fluctuated over time. Jets would flare up, then shut off. Material would burst forth in violent surges rather than flow in a continuous stream. And that brings us to the present. The latest observations, captured by Michael Jaeger on November 8th, show another dramatic change in the comet's behavior. 3I Atlas is erupting again, but this time the eruption is far more complex than anything seen before. Look closely at the image. You'll notice 5 distinct jets, one shooting forward, another rising upward, and 3 spreading outward at varying angles. Each of these plumes marks a different eruption point, separate vents on the comet's surface, where trapped gases built immense pressure until they finally tore through. The forward jet is the brightest, sharply defined and stretching several hundred kilometers before fading into the comet's glowing coma. The upper jet is dimmer and more diffuse, like a thin plume dispersing as it rises. The side jets, fainter still, are barely visible without enhanced imaging, but they're there quietly adding to the spectacle. And all of this is happening simultaneously. Now here's where things become fascinating. For several weeks, we've had almost no clear observations of 3I Atlas. It was hidden behind the sun, invisible from Earth. Spacecraft like ESO and Stereo tracked its position through coronagraphs. But those instruments only record brightness and general motion, not fine surface detail. A handful of Mars orbiters caught glimpses during the October 3rd flyby. The ExoMars Trace Gas Orbiter and Mars Express both turned their cameras toward the passing comet. The results showed little more than a glowing blur, a faint coma, no structure visible. The Mars Reconnaissance Orbiter, equipped with its powerful HiRISE camera, could have given us far clearer imagery, but those files haven't been released. Due to the US government shutdown, much of that data remains inaccessible, so for weeks we've been effectively blind. Until now, Michael Jaeger's latest photograph offers our first detailed view of 3I Atlas since it re-emerged from behind the sun. And what it shows is astonishing. The comet has completely transformed. It's no longer the calm, quiet traveler we saw in July and August, the one that mystified astronomers with its anti-tail and metallic oddities. It's now violently active, and understanding why has become our new challenge. Here's what's likely happening. As 3I Atlas approached perihelion on October 29th, it absorbed an immense amount of solar radiation. At a distance of 1.36 astronomical units, sunlight delivered roughly 33 gigawatts of power onto the comet's surface, equivalent to the total nuclear energy output of the United States. That energy didn't just warm the surface, it began to penetrate deeper. Although rock and ice are poor heat conductors, they slowly allow warmth to creep inward. As that heat travels below the surface, it eventually reaches pockets of volatile ices, carbon dioxide, methane, ammonia, that have been trapped for eons. When those ices begin to sublimate, gas pressure starts to build. Imagine a sealed pocket of CO2 buried under dust and gravel. As the sunlight seeps in, the ice transforms into gas, but there's nowhere for it to go. The pressure climbs higher and higher, until finally the crust cracks open. The trapped gas explodes outward, carrying dust and debris with it, forming the brilliant jets we now see. Each jet marks a fracture, a rupture where subsurface gas overcame the crust's resistance. Because the comet is spinning, these jets sweep around like rotating spotlights, creating intricate light patterns, and giving the impression of complex shifting structure. This is normal cometary behavior, but what's unusual is timing. Why did the eruption happen now, not during the height of perihelion, when solar heating was most intense? One possible explanation: thermal delay. The heat might have taken time to reach the right depth below the surface, igniting buried ice only days after the comet's closest solar pass. Another idea: rotation exposure. The vent sites may have been hidden in shadow during perihelion, only rotating into sunlight weeks later, triggering sudden sublimation. Or perhaps the crust itself simply gave way, gradually weakening from constant stress until it fractured on November 8th, releasing the pent-up gases in a massive multi-directional burst. We can't be certain which explanation is right, but what's undeniable is this: 3I Atlas is now far more active than anyone predicted, and its eruption is unfolding right as it moves deeper through the inner solar system, nearing a point where Earth-based telescopes will soon have a perfect view. So the next question is, what comes next? Chapter 5, the solar environment and its impacts. To understand the jets, we need to understand the environment 3I Atlas has endured over the past several months. The sun is no calm star. It's a raging ocean of plasma, constantly convulsing and erupting with magnetic fury. Solar flares flash across its surface. Magnetic loops twist and snap. And when the tension becomes too great, coronal mass ejections, massive clouds of charged particles are hurled into space, carrying billions of tons of superheated plasma. 3I Atlas has been flying directly through this chaotic environment. On October 21, 2025, it reached superior conjunction, passing directly behind the Sun from Earth's perspective. At that exact moment, the comet was bombarded by peak solar activity. Using data from ESO-SO's LASCO C3 coronagraph, scientists pieced together what happened in those critical days before and after perihelion. On October 21st, a massive CME, a coronal mass ejection, erupted from the Sun's far side, and it was aimed squarely at 3I. That CME carried a shockwave of plasma racing outward at hundreds of kilometers per second. When it slammed into the comet, it didn't destroy it. Comets, though small, are surprisingly resilient, but it did have a major effect. The impact would have compressed the comet's magnetic field, the invisible region where solar wind interacts with the comet's outflowing gases. This magnetic region, the magnetar pores, typically has a field strength around 50 nanotella under calm solar conditions. But during a powerful storm, that can spike to 300 nanotella or higher. We know this because the ESA's Rosetta spacecraft observed a similar event in 2014, when a solar storm struck Comet 67P. Its instruments recorded a dramatic surge in magnetic intensity. It's very likely that 3I Atlas experienced the same. Though we lack a probe nearby to measure it directly, the coronagraph imagery tells the story. Multiple CMEs colliding with the comet's position. October 21st, the first major blast. October 24th, another one. October 26th, more eruptions followed. And all of this was happening as 3I Atlas passed through perihelion, soaking up the sun's full energy output. So what does that mean? When a solar storm strikes a comet, it doesn't just squeeze its magnetic field, it also superheats the coma, the cloud of gas surrounding the nucleus. The plasma within a coronal mass ejection is unimaginably hot, millions of degrees. When that searing plasma slams into the gas and dust surrounding a comet, it doesn't just pass by, it energizes everything it touches. Atoms get ionized, electrons are ripped away, and powerful shock waves ripple outward through the coma, the comet's hazy envelope. All that energy has to go somewhere. Some escapes into space as radiation, but much of it gets trapped, absorbed by the comet itself. The surface warms, the subsurface layers heat up, and the entire structure becomes more volatile. So when those solar storms struck 3I Atlas, they didn't just collide with it, they supercharged it. They dumped immense amounts of energy into a body that was already teetering on the brink of instability. And it's possible, perhaps even likely, that this final energy surge was the spark that ignited the outburst we're now witnessing. Think about the timeline. For weeks, the comet soaked in sunlight, its outer crust heating, while deeper layers slowly absorbed that warmth. Gases trapped beneath the surface began to vaporize. Pressure built, yet somehow the crust held firm until the solar storms arrived. Those storms unleashed a blast of high-energy particles and plasma that may have tipped the balance. The added heat and pressure could have been just enough to push the comet past its critical threshold. The crust fractured, the gases burst outward, and jets of material erupted into space. The spectacle now visible in telescopic images. Of course, this is still speculative. We don't have direct temperature readings from 3I Atlas's surface, nor do we know precisely how much energy those storms delivered. But the sequence of events fits remarkably well. Solar storms in late October, followed by a dramatic eruption in early November. The timing feels too aligned to ignore. And this brings us to an often overlooked piece of the puzzle, the plasma environment that surrounds every comet. When most people imagine comets, They picture icy bodies streaking through space, shedding gas and dust in a bright, glowing tail. But there's an unseen force at play here, a sea of plasma enveloping the comet, shaping its interactions with the solar wind. Here's what happens. As a comet moves closer to the sun, it's bombarded by ultraviolet radiation, X-rays and streams of energetic particles. These photons are powerful enough to knock electrons away from atoms and molecules within the coma, transforming neutral gases into charged ions. This process, known as photoionization, never stops. Every molecule of water, carbon dioxide, or even trace metals like iron or nickel is constantly getting hit, losing electrons and becoming part of this charged cloud. What you end up with is a living, shifting plasma envelope surrounding the nucleus. But the story doesn't end there. The solar wind, a constant flow of plasma from the sun traveling hundreds of kilometers per second, interacts with this ionized cloud. As it crashes into the coma, it slows down, bends, and creates a shock front, a bow-shaped wall of compressed plasma that forms in front of the comet, similar to the bow wave formed by a ship cutting through the sea. Behind the comet trails another structure, the ion tail. This tail is made of charged particles, ionized molecules of water, CO2, carbon monoxide, all being swept away at tremendous speed by the solar wind. It's long, narrow, and perfectly straight, always pointing directly away from the sun. And when sunlight strikes those ions, they glow. Carbon monoxide ions shimmer blue, others in subtle hues, creating that hauntingly beautiful, ghost-like tail that can stretch for millions of kilometers. We've seen this countless times before. Hale-Bopp in 1997 boasted a spectacular ion tail visible to the naked eye. McNaught in 2007 did the same, but with 3I Atlas, that signature blue tail hasn't yet been clearly observed. We see its broad, dusty fan, yes, but the faint plasma tail, not yet. Or perhaps it's there, hidden beyond our current observations, waiting for the right instruments to reveal it. Ion tails are notoriously difficult to detect. They require specialized spectrographs, tools that can isolate the faint emission lines produced by glowing ion. And since 3I Atlas spent weeks hidden behind the sun, astronomers simply haven't had the opportunity to observe it under optimal conditions. That's about to change. In the coming weeks, as the comet climbs higher into the early morning sky, telescopes equipped with sensitive spectrographs will finally turn toward it. These observations will help scientists measure the precise composition of its coma and search for signs of that elusive ion tail. If found, it could tell us a lot: how rapidly the comet is losing material, how strongly it interacts with the solar wind, and whether it behaves like a typical comet or continues to defy expectation. But there's an even deeper reason scientists are fascinated by a comet's plasma environment. Plasma carries information. When the solar wind collides with the ionized gases around a comet, it doesn't just blow material away. It sets off a complex interplay of electromagnetic force. Electric currents begin to flow. Magnetic fields twist and wrap around the nucleus like invisible threads, creating distinct regions within the comet's plasma bubble. There's the ionopause, where the solar wind gives way to the comet's own ionosphere. There's the magnetopause, the zone where the comet's induced magnetic field peaks. And of course, the bow shock, that outer frontier of compressed plasma bracing against the solar wind. Each of these layers behaves differently, shaped by the balance between incoming solar pressure and the comet's outgassing force. Inside these boundaries, charged particles don't move randomly. They can become trapped, accelerated, or heated, their energies rising in waves and pulses. So imagine what happens when a powerful solar storm, like the ones that hit 3I Atlas in late October, sweeps through this delicate structure. The entire plasma bubble contracts, its bow shock collapsing closer to the comet's core. The magnetic fields intensify, and when the storm passes, everything expands again, a violent push-pull cycle, like a spring under tension. This constant compression and release generates turbulence. Waves ripple through the plasma, particles get slingshotted to extreme speed. Some of these high-energy electrons, protons and ions, slam directly into the comet's surface, adding yet another layer of heat and pressure below its crust. So the storms didn't just warm 3I Atlas with radiation. They bombarded it with streams of charged particles moving at near-relativistic speeds. That bombardment may have been the final catalyst, the invisible trigger that set off the chain reaction, leading to the comet's eruption. Again, it's worth emphasizing, this remains a hypothesis. We don't have instruments in place to directly measure these plasma interactions around 3I Atlas, but drawing from what we've learned from missions like Rosetta, at Comet 67P, and others, this explanation fits the pattern. It's grounded in what we already know, and it paints a compelling picture of a comet pushed beyond its limits by the raw forces of the sun. The Rosetta mission revolutionized our understanding of how comets interact with the solar wind. It revealed a plasma environment that's far from simple, turbulent, ever-changing, and full of unexpected behavior. And right now, 3I Atlas has been journeying through one of the most active solar environments our era has seen. So it isn't far-fetched to think that these plasma interactions played a significant role in what we're witnessing today. The sudden eruption, the multiple jets, the dramatic surge in activity, all of it may trace back to the intense solar storms that battered the comet in late October. But to truly grasp what's happening, we have to look deeper inside the comet itself. Chapter 6: The Structure and Composition Mysteries. To understand 3I Atlas, we must ask, what is it made of? Because its composition holds the key to why it's acting this way. Spectroscopic data reveals that 3I Atlas is particularly rich in carbon dioxide. It contains water ice as well, but in lower amounts compared to most comets born in our solar system. It's also releasing nickel and trace metals, an unusual finding. But beyond these chemical clues lies a bigger question. How is all that material arranged inside? Is 3I Atlas a solid block of frozen ice, or is it more of a loose rubble pile, a cluster of icy grains and dust clumped together under its own faint gravity? Is it uniform from core to crust, or does it have layers perhaps like the rings of an onion, each preserving a different history? These questions aren't trivial. The internal structure determines how heat moves through the comet, and heat flow controls when and where ice turns to vapor, the process that fuels the jets and eruptions. For example, if the comet's nucleus were a dense, solid chunk of ice covered by a thin crust of dust, then solar heat would seep inward very slowly. It could take days or even weeks for that buried ice to warm enough to sublimate. When it finally does, gas pressure would build beneath the crust until, suddenly, the surface bursts open in an explosive eruption. That's one scenario. Now imagine the opposite, a porous nucleus riddled with cracks and voids. In that case, sunlight would penetrate much faster. Heat could reach deeper pockets of ice quickly, and gases could escape more easily through those cracks, without building up the kind of pressure that causes violent blowouts. Instead, you'd get gentle, continuous outgassing rather than dramatic eruptions. So where does 3I Atlas fit? Based on what we've observed, it seems to fall somewhere in between. It's not completely solid, otherwise we wouldn't have seen any activity as early as May and June, when it was still far from the sun. But it's not entirely porous either. If it were, we'd expect a steady release of gas all the time, not the sporadic bursts we've seen. Instead, it's likely a mosaic of materials, some regions dense and compact, others loose and fragile, some rich in ice, others stony or dusty. As the comet rotates and travels through space, different areas face the sun, heating at different rates and triggering activity in irregular patterns. This uneven structure could explain everything. The strange anti-tail that appeared in August and later vanished, the sudden spikes of water vapor in September, the unexpected bursts of iron emissions, and the chaotic jets we're seeing now. All signs point to one conclusion. 3I Atlas has a complex, heterogeneous interior, a comet built from patchwork layers and surprises. But here's where it gets even more fascinating. 3I Atlas isn't just any comet, it's an interstellar one. And that changes everything. When a comet forms within our solar system, it's built from the ingredients found in the protoplanetary disk, the vast swirl of gas and dust that once surrounded our young sun. That disk had its own specific recipe of elements and molecules, reflecting the conditions in this particular corner of the Milky Way roughly 4.6 billion years ago. But 3I Atlas didn't form here. It was born around another star in another solar system, under entirely different cosmic conditions. Maybe that parent star was richer in carbon. Maybe its surrounding disk was colder, allowing different ices to condense. Maybe its local chemistry favored compounds rarely seen in our neighborhood. The evidence we do have gives us some clue. The comet's high concentration of CO2, suggests it originated in a very cold environment, one cold enough for carbon dioxide to freeze readily, while water ice remained less abundant. That tracks with what we know about CO2. It solidifies at lower temperatures than H2. The metallic signature, strong nickel without corresponding iron, is harder to explain. One possibility is that its parent star had an unusual chemical makeup, perhaps a population 2 star, an ancient stellar type that formed before heavier elements like iron became common in the galaxy. Another idea is that during formation, nickel and iron were separated by chemical or physical processes in its home disk, perhaps forming distinct zones where each metal condensed separately. Whatever the case, one thing is clear. 3I Atlas carries a chemical fingerprint from another star system. It's literally a messenger from a world we'll never reach. A frozen sample of alien chemistry drifting through our solar system. By studying it, we're peering into the conditions of a distant region of the galaxy billions of years ago. That's astonishing. But there's a catch. 3I Atlas hasn't been in deep freeze all this time. It's spent billions of years traveling through interstellar space, and interstellar space is not empty. It's filled with a rain of high-energy particles, cosmic rays, streaming through the galaxy at near light speed. These protons, helium nuclei, and heavy ions come from the most violent events in the universe: supernovae, pulsars, even black holes. When a cosmic ray slams into a comet, it doesn't bounce off. It penetrates deep into the ice and rock, colliding with atoms and creating secondary particles. It breaks molecular bonds, rearranges chemical structures, and forges entirely new compounds. Over eons, this relentless bombardment transforms the comet's outer layers. Scientists estimate that the top 15 to 20 meters of 3I Atlas's surface have been heavily altered by cosmic radiation. Carbon monoxide can be converted into carbon dioxide, complex organic molecules can form. The very structure of the ice itself can change, becoming more porous, more fragile. That means when we observe 3I Atlas, we're not seeing a pristine, untouched sample from its home system. We're seeing something more like a weathered relic, a cosmic time capsule that's been left out in the galactic elements. Still precious, still full of secrets, but altered by time and radiation. This detail might also explain why the comet's eruptions happened when they did. If the outer layers have been chemically and structurally weakened by cosmic rays, they could be more brittle and unstable than the deeper, untouched material beneath. As sunlight warmed these processed layers, sublimation would begin, gases would accumulate, and the fragile crust, already riddled with microscopic fractures, would finally give way. Another intriguing possibility is that cosmic rays didn't just weaken the surface, they changed its chemistry in unexpected ways. Perhaps they created pockets rich in volatile compounds like CO2, converted from those isolated pockets could heat unevenly and sublimate explosively, leading to the kind of sudden jets we've been observing. It's all still theoretical, but it's the kind of educated speculation that fits what we know about comets, about cosmic radiation, and about the physics of interstellar travel. And together, these clues give us a framework for understanding why 3I Atlas is so unpredictable, so unlike any comet we've seen before. But even as scientists piece together this logical explanation, there's another layer to the story, a louder one, echoing through online forums and late-night discussions. Speculation, wild theory, and a question that keeps resurfacing no matter how many times experts address it: is 3I Atlas natural or is it something else entirely? Chapter 7. The Artificial Hypothesis. Let's start with something absolutely clear. The overwhelming consensus among astronomers and planetary scientists is that 3I Atlas is a natural object, a comet, a frozen relic of rock, dust, and volatile ices that coalesced billions of years ago around some distant star. That's what the spectral data indicates. That's what every observation up to now has reinforced, and that's what Occam's razor would suggest. The simplest explanation, the one that requires the fewest assumptions, is most often the correct one. But, and there's always a but, not everyone is convinced that the full story ends there. From the moment 3I Atlas entered our awareness, a handful of researchers began to wonder whether its bizarre characteristics might hint at something far more profound than a mere interstellar comet. One of the most outspoken voices in this conversation is Harvard astrophysicist Avi Loeb. You might remember him from the Oumuamua debate back in 2017, when that first known interstellar object streaked through our solar system. Loeb famously proposed that Oumuamua might not be a rock at all, but rather an artificial construct, possibly a light sail, a thin reflective sheet designed to harness solar radiation for propulsion. Most of the scientific community disagreed, suggesting that Oumuamua's oddities, its elongated shape, tumbling spin, and slight acceleration as it exited the solar system, could still be explained by natural physics. Perhaps it was an unusually shaped fragment of an ancient comet, its volatile materials depleted, but still behaving within the boundaries of nature. Now, years later, Loeb has turned his attention toward 3I Atlas, and this time, he's not alone. In a paper released in July 2025, Loeb and his co-authors outline several features of 3I Atlas that, in their view, don't quite align with the standard comet model. Let's go through them one by one. First, the trajectory. 3I Atlas entered the solar system with an orbital plane tilted only about 5 degrees from the ecliptic, the same flat plane along which all major planets orbit. Statistically, that alignment has only about a 0.2% chance of occurring purely by coincidence. Not impossible, but certainly rare. Second, the planetary encounters. 3I Atlas passed unusually close to Mars on October 3rd. It's expected to pass near Venus soon after, and then near Jupiter in March 2026. According to Loeb's probability estimates, the odds of all three close approaches happening randomly are roughly, again not impossible, but improbable. Third, the timing of perihelion. The comet's closest approach to the Sun, its perihelion, occurred on October 29th, at a point directly opposite the Sun from Earth's perspective. In other words, the most critical phase of its journey happened while it was completely hidden behind the Sun, unobservable from Earth-based instruments. Coincidence? Possibly, but it raises questions. Fourth, the absence of non-gravitational acceleration. Despite all the visible signs of outgassing, carbon dioxide jets, sublimating ice, metal emissions, 3I Atlas shows no detectable deviation from a purely gravitational orbit. Typically, as a comet releases gas, the reactive force slightly alters its path. Yet, this one moves as if it's solid, incredibly massive, and undisturbed. The estimated mass exceeds 33 billion tons, far denser than a typical comet's loosely packed rubble pile composition. Fifth, the chemical composition. Spectroscopic data reveal nickel without iron, an unusually high CO2 ratio, and a sudden surge of water vapor at distances where a comet shouldn't yet be active. Each anomaly can be explained individually, but together they stretch conventional models of comet chemistry to their limit. 6. The anti-tail, a narrow jet pointing toward the Sun, instead of away from it, with material seemingly flowing in the wrong direction. While not impossible, anti-tails can occur due to viewing geometry or complex dust ejection patterns. It remains highly uncommon. 7th, the brightness. Multiple independent observations show that 3I Atlas is reflecting more light than expected for its size. It's either coated with an unusually reflective material, perhaps metallic, crystalline, or glass-like, or more intriguingly, it might be emitting light of its own. 8th, the WOW signal connection. Back in 1977, a powerful, unexplained radio signal was detected by the Big Ear Observatory in Ohio. It lasted just 72 seconds before vanishing. That signal's origin point lies about 9 degrees from the same region of the sky where 3I Atlas entered the solar system. Coincidence? Almost certainly, but, as Loeb notes, it's a curious alignment worth at least mentioning. Now, to be clear, Loeb doesn't claim that 3I Atlas is artificial. He speaks in probability. In his latest estimates, he assigns roughly a 30 or 40% likelihood that 3I Atlas may not be entirely natural, that it could contain some form of engineered structure, possibly a probe, a derelict spacecraft, or a fragment of advanced technology launched by an intelligent civilization long ago. And if that's true, if hypothetically, 3I Atlas does contain some technological component, then the current eruption we're witnessing might not be random outgassing at all. It could be something deliberate, a signal, a maneuver, or even a deployment event. Let's pause here for an important clarification. This is not mainstream science. The overwhelming majority of planetary scientists and astronomers firmly reject the artificial hypothesis. They argue that every one of Loeb's so-called anomalies can be interpreted through the lens of natural physics and chemistry. The trajectory alignment? Statistically rare, yes, but our galaxy is flat, and so is our solar system. It's not shocking that an object ejected from another star's planetary plane would align somewhat with our own. The planetary flybys? The inner solar system is dense with planets. Close encounters are bound to happen. The lack of acceleration. Maybe the comet's density is higher than assumed, or perhaps the outgassing is occurring in balanced directions, cancelling out any measurable thrust. The chemical oddities, interstellar comets, should be unusual. They formed under entirely different stellar conditions. The anti-tail, likely a result of geometry and rotation. The brightness could be surface reflectivity, or a miscalculated size. And the wow signal, most likely terrestrial interference, or a natural radio reflection. The positional overlap is almost certainly meaningless. That's the dominant view. To most experts, 3I Atlas is still a comet, a fascinating, unpredictable, and alien one, but a comet nonetheless. Yet, despite all that, something about this object keeps evading tidy explanation. Every time researchers think they understand it, it shifts again, producing new phenomena that seem to defy its own profile. The anti-tail appearing and disappearing, the water vapor erupting unexpectedly, the iron traces emerging from nowhere, and now multiple jets firing simultaneously, forming intricate geometric patterns across its coma patterns that almost seem intentional. I'm not saying it is designed, but visually and behaviorally, it looks engineered. And that's worth paying attention to, not because we want it to be alien, but because science demands curiosity, not complacency. The goal isn't to cling to the simplest answer, it's to follow the evidence wherever it leads, even if that means entertaining the uncomfortable, the improbable, or the extraordinary. Now bringing this back to the present moment, right now 3I Atlas is actively venting material, plasma, gas, dust, into space in a spectacular display. That's not theory, that's observational fact. We have images, we have spectra, we have data. The question that remains is simple, yet profound. What happens next? Chapter 8. What happens next? Observations and projections. In the weeks ahead, 3I Atlas will rise steadily in the pre-dawn sky. By mid-November, it will have moved far enough from the sun's blinding glare that telescopes across the northern hemisphere will finally gain an unobstructed view. When that happens, the next chapter in this story will begin. One written not in speculation but in hard data.